Welcome back to the deep dive. We spent so much time lately talking about the brains of the AI revolution, the GPT-4s, the Llama 3s, the DeepSeeks. But today, we are pivoting.
We are?
We're going to look at the nervous system that actually lets those brains function.
It's a classic infrastructure story, isn't it?
Yeah.
Everyone looks at the race car. Nobody looks at the highway or the fuel injection system.
Right.
But without those, the car is just a statue.
And that is so literal in this case. We're looking at a stack of reports on large model inference frameworks. Now, that sounds technical, but the headline finding here is, it's startling.
It really is.
It suggests that despite these models having what they call emergent abilities, writing code, poetry, reasoning, they're currently being strangled by a really basic bottleneck.
The memory wall.
The memory wall, exactly, the computing paradox. We have these models that cost billions to train, but when we actually try to run them, what we call inference, we hit a wall. Why is just running the model so much harder than it seems?
Well, it really comes down to a big shift in the industry. For years, the only question was, how many GPUs do I need to train this thing?
Right, a brute force problem.
It's a brute force math problem.
Yeah.
But now we've moved to industry application. So the question is, how do I serve this model to 10 million people at once without going bankrupt? And it turns out the traditional way computers handle memory is completely unsuited for LLMs.
Okay, so the report throws out a number that I had to double check. It says that before the modern frameworks we're talking about today, like vLLM, traditional GPU memory utilization was often less than 20%.
20%. It's shocking, isn't it?
Yeah.
Imagine buying a data center full of H100s, and these are, what, $30,000 chips?
Yeah.
And they're just sitting idle 80% of the time. Not because they aren't computing, but because they are just waiting for memory space.
So, okay, before we get to the solutions, the vLLMs and the SGLangs of the world, we need to understand the villain here. Why is text generation such a memory hog? The research breaks it down into two stages, prefill and decode. Can you walk us through that?
Yeah, so stage one is prefill. This is when you type your prompt into, say, ChatGPT. The model reads your entire question all at once. This part is actually pretty efficient. It's what we call compute bound.
So the GPU is just crunching numbers.
As fast as it can. So reading is fast.
Okay, reading is fast.
Writing is the problem. That's the decode stage. The model generates the answer one word or, one token at a time. But here's the catch. LLMs are stateless by default.
What does that mean?
They don't remember what they just wrote unless you feed it back to them.
You're kidding. So for every single new word it generates, it has to reprocess everything it has already written, plus my original question.
Effectively, yes. It needs to keep all that context, what's called the key value cache or KD cache. It has to keep it stored in the GPU memory. And as the answer gets longer and longer, that cache just grows.
And the problem, I'm guessing, is we don't know how long the answer will be ahead of time.
Precisely. If I ask, who is the president? The answer is what? 2 words. If I ask, write an essay on the history of democracy, it's 2,000 words.
Right.
So traditional systems were terrified of running out of space. They would reserve this massive single block of continuous memory, enough for the longest possible answer, just in case.
It's like a restaurant refusing to seat a couple at a 4-top table because, they might eventually invite 2 friends, so the table just sits half empty.
That is the perfect analogy. That's exactly what memory fragmentation is. You have all these tables, these memory blocks, reserved but totally empty. And that's where your 20% efficiency comes from.
You're blocked by your own reservation system.
Exactly.
So this is the problem statement. The mission of this deep dive is to explore the operating systems that solve this. We have the industrial giants, vLLM, SGLang, and then the tools for the rest of us, like Ollama. Let's start with the throughput king. Let's talk vLLM.
vLLM is effectively the industry standard right now. If you're using a commercial API, there is a very, very high chance vLLM is running underneath it all.
And their big breakthrough was what?
Their breakthrough was looking at this memory problem and saying, wait a second, operating systems solved this decades ago.
And they call it PagedAttention.
PagedAttention, right. Think about your laptop's RAM. When you open a web browser, the computer doesn't hunt for one giant, unbroken block of physical memory, right?
No, of course not.
It breaks the data into these tiny pages and just stuffs them wherever there's room. It's like playing Tetris with your data.
So vLLM just applies that same logic to the GPU.
Exactly. It breaks that growing key value cache into these fixed-size blocks. They don't need to be next to each other.
Yeah.
vLLM just creates a lookup table, a sort of map. So the model thinks the memory is continuous, but physically it's scattered all over the place.
And the report says this drops memory waste from that, just horrifying, 60 to 80% down to under 4%.
Which is, I mean, it's massive. It means you can fit way more conversations into the same GPU memory. And because you aren't wasting all that space, you unlock the second superpower of vLLM.
Which is continuous batching.
Continuous batching.
Yeah, I like the analogy the report used here about the bus.
It's a perfect way to visualize it.
Yeah.
Old systems used static batching. So imagine a bus that waits until every single seat is full before it leaves the station.
Okay.
And worse, it can't let anyone off until the person with the longest trip gets to their final destination.
So if I ask a short question and you ask a long one, I'm just stuck on the bus waiting for you to finish your whole essay before I can get my one-word answer.
Exactly. It just blocks the whole line. vLLM introduces a dynamic bus. It schedules at the token level. The moment my request is done, my seat is empty, and vLLM instantly slots a new person in.
Even if other people are still on their trip.
Yep. It's totally asynchronous. The V1 engine upgrade they mentioned in the report takes this to an extreme. We're talking microsecond level scheduling. It basically eliminates any of the overhead or decision-making time.
So the takeaway for vLLM is it's the muscle. It's all about volume.
That's it. If you have, say, 50 or more people hitting your server at the same time, vLLM is almost certainly the winner. It prioritizes throughput, just getting as many people served as possible.
But then we have SGLang. The report frames this one very differently. If vLLM is the generic operating system, SGLang is described more like a specialized compiler. What's the distinction there?
That's a great distinction. While vLLM optimizes for space, SGLang optimizes for structure and reuse. It's tackling a whole different bottleneck redundancy.
And this brings us to their proprietary tech, RadixAttention.
Right. Think about how most business applications use AI. They usually start with a long system prompt.
Oh yeah, like, you are a helpful customer service agent for Bank of America. Here are our policies.
Exactly. And that whole preamble is sent with every single user request.
Every single time.
Correct. In vLLM, generally speaking, the model reprocesses that preamble every time a new request comes in. It's just doing the same math over and over and over. SGLang uses what's called a radix tree. It's a data structure that maps the conversation flow.
Okay.
It recognizes, hey, I've already calculated the math for this Bank of America intro.
So it caches the thought process, not just the text itself.
That's a perfect way to put it. It keeps the mathematical state of that prefix in memory. So if a new request comes in that matches that prefix, it just skips the computation entirely and appends the new question.
The report mentions this is a total game changer for RAG retrieval augmented generation, where you're dumping huge documents into the prompt.
Huge. The statistic in the report is that for these complex multi-turn conversations, SGLang reduces the time to first token. That's how long you wait for the answer to start generating.
That initial pause.
That pause, yeah. It reduces it by 3.7 times compared to vLLM.
Wow. That's the difference between a pause that feels natural and a pause where you think the website crashed.
It really is.
Yeah.
But SGLang has one more trick that I think is maybe even more important for developers. Structure generation with something called CFSM.
CFSM. Okay. Compressed finite state machine. That is a mouthful.
It is, but the concept is brilliant. One of the biggest headaches with LLMs is just getting them to follow rules, right?
Absolutely.
If you ask an AI to output data in a perfect JSON format for a database, it might, I don't know, hallucinate an extra comma or add a polite, here is your code at the beginning.
Which breaks the whole parser. So usually developers use masking to fix this. They force the model to only pick valid characters.
But masking is really slow. It forces the model to calculate the probability of every possible token. Then it just zeroes out the bad ones. SGLang takes a different approach. It knows the structure of JSON. It knows that after, say, name, there must be a string.
So it doesn't even ask the model what comes next.
It skips the prediction entirely for those inevitable parts. It just inserts the required syntax and only uses the GPU to predict the actual content. It jumps forward in the state machine.
It feels a bit like autocomplete on steroids.
It's a highly efficient constraint. And the report says this makes generating that structured data about 3 times faster because you aren't wasting compute on formatting characters.
So if I can just summarize the server wars section then. If I'm Netflix and I have 100,000 users asking random questions about movies, I want vLLM for the sheer throughput.
Yes. High concurrency, lots of random inputs. vLLM is your highway.
But if I'm building, say, a legal bot that processes 50-page contracts and has to output a strict JSON summary every time.
SGLang, hands down. The cache reuse for the contract, that's RadixAttention, and the speed of the JSON output from CFSM makes it vastly superior. Plus, on smaller scales, SGLang saves about 47% more memory on 8B models, so it's cheaper to run.
Okay, so that's the cloud, that's the enterprise level. But one of my favorite parts of this deep dive was the section on local deployment. The idea that we can run this stuff on a generic laptop, it still just blows my mind.
It's the democratization phase, really. We are moving from H100s in a server farm to the MacBook Air on your desk.
But how is that even possible? A year ago, these models were, what, 300 gigabytes?
It all starts with a project called llama.cpp and a file format you might have seen around called GGUF.
GGUF, I see that everywhere on Hugging Face.
Think of GGUF as the MP3 of AI.
Yeah.
Before MP3s, audio files were massive, right? MP3s compressed them with minimal loss of quality. GGUF does that for models using quantization. But the real magic of llama.cpp is how it manages the hardware.
The report talks about offloading.
Right. Your laptop probably has a pretty fast GPU, but it doesn't have much video memory, maybe 8 or 16 gigs, but you have plenty of slower system RAM.
Okay.
Offloading lets llama.cpp slice the model. It puts the most critical layers on the fast GPU for speed, and then the rest just overflows into your system RAM.
So it doesn't crash if you run out of video memory.
No, it just gets a little bit slower. It manages that split seamlessly,
Right.
and it uses memory mapping, which lets it start running the model before it's even fully loaded into RAM. It just reads from the hard drive on demand.
So llama.cpp is the engine that makes all this possible. But most listeners aren't going to be running code from the command line. They're using the tools built on top of it, the two big ones being Ollama and LM Studio.
And they serve two very different psychological needs, I think.
Ollama feels like it's built for the builders. The report compares it to Docker, which feels right.
Yes, Ollama runs as a background service. It's headless. And its superpower is the model file.
This is so cool. It's like a recipe.
It's exactly like a recipe. You can take a generic model like Llama 3, give it a specific system prompt like, "You are a grumpy editor who hates adverbs," and save that entire configuration as a new model.
Oh, wow.
Then you can just call that custom model from the code in your app. It's really designed for integration.
Whereas LM Studio feels more like a laboratory.
LM Studio is the explorer's choice. It's a full graphical interface. You have the chat window, but on the right side, you have all these sliders and graphs. You can manually adjust how many layers go on the GPU. You can see real-time charts of your RAM usage.
I've used it to compare models. You can load two different models and ask them the same question right next to each other.
It's fantastic for learning. You can visually see the trade-offs. You can tweak the temperature, which controls creativity, and see immediately how it changes the answer. You want to understand how these things work, LM Studio is the best classroom you can get.
So we have the present landscape covered. vLLM and SGLang are fighting it out in the data center. Ollama and LM Studio are handling the edge. But the report wraps up with the cutting edge. What is the next bottleneck we need to break?
I think the future is all about doing more with less. We're seeing a massive push into quantization.
We touched on that with GGUF, just shrinking the model. But the report mentions something called AWQ.
Activation-aware weight quantization. It's a mouthful, but the concept is really intuitive. Think about the human brain. Not every single neuron is firing for every single thought, right? Some connections are crucial, others are just background noise.
So AWQ figures out which parameters in the model are actually doing the heavy lifting.
Exactly. It identifies the salient weights,
Yeah.
the critical 1%, and keeps them in high definition. Then it aggressively compresses the other 99%.
It's like compressing a JPEG image, but making sure to keep the eyes of the person perfectly sharp while the background gets a little blurry.
That's a great analogy.
Yeah.
And when you combine that with new hardware formats like FP8 coming in NVIDIA's Blackwell chips, we could see memory usage drop by another 50%.
Which effectively doubles the intelligence we can fit on our current hardware.
Or doubles the speed. And speaking of speed, the other huge trend is speculative decoding. This addresses that decode bottleneck we started with, that slow word-by-word generation.
The report explains this using a draft model.
Yes. So imagine you are typing on your phone, and the autocorrect suggests the next 3 words.
Okay.
You just tap accept, accept, accept. That's way faster than typing all the letters.
Right. So the system uses a tiny, kind of dumb, but really fast model to guess the next few words.
Correct. The tiny model basically shouts out, "The cat sat on the..."
Yeah.
And then the big model, the genius, looks at that whole sequence and validates it in one single step. It just says, yep, those are all right.
So instead of running the big model 4 times for 4 words, you run it once to check the work of the little guy.
Precisely. The report mentions the EGLE2 and 3 algorithms that are implemented in SGLang. They're seeing 2 to 3 times speed improvement without losing any quality because the big model still has the final veto power.
That's just incredibly clever. It feels like the software is finally really catching up to the hardware.
It is. And we are seeing a convergence. The report predicts that these frameworks will start acting less like simple runners and more like compilers. They'll analyze your specific prompt, look at the model's structure, and optimize the execution path in real time.
So bringing this all back to the listener, we've covered a lot of acronyms today. How should they navigate this? What's the takeaway?
I'd simplify it like this. If you are a developer building a public-facing app and you expect traffic, you need vLLM. It's the stable, high-throughput highway.
And if you're building a complex agent that needs to generate code or JSON or handle difficult reasoning tasks,
It's SGLang. The structure and the caching are just unmatched there.
and if you're just a curious human being who wants to keep their data private and see what this stuff can really do,
Download LM Studio or Ollama. Seriously. Just running a 70 billion parameter model on your own hardware is a feeling of power, that is. It's hard to describe.
it really is. But I want to leave us with one final thought from the source material that I found kind of provocative.
The reasoning engine.
Yes. We've been talking about inference as just generating text. Next token, next token, next token. But we're starting to see models like DeepSeek R1 that think before they answer.
Test time compute. They generate these internal monologues, do recursive searches, self-checks, all before they output the final answer.
And if that becomes the norm, our inference engines can't just be memory managers anymore, can they?
No, they'll have to evolve. They won't just be managing pages of memory, they'll be managing thought processes. They might need to pause generation, allocate more compute to a hard logic problem, and then speed up for the summary.
We're moving from managing a printing press to managing a mind.
That really is the next frontier. And if history is any guide, the software will adapt to make it happen.
A fascinating look at the engine room. I hope this deep dive helped you understand what is actually happening when you hit enter on that prompt. Go download a local model and try it out.
You won't regret it.
Thanks for listening. We'll see you in the next deep dive.